I'm Rick Huang. I develop AI solutions for different industry verticals and use cases. Also, working with ISVs and consulting firms in Netapp AI Partner Network.
This is how Netapp AI solutions can accelerate your journey to AI.
Today, I'm joined by Egor Kharakozov from SFL Scientific. We're excited to share with you our integrations for AI in healthcare. Welcome, Igor.
Hi, my name is Egor Kharakozov. I'm a data scientist and developer, and as a consultant with SFL Scientific, I've worked on numerous projects designing and implementing custom NLP and computer vision solutions for clients big and small across various industries. So as Rick mentioned, I'm going to give a quick overview of this use case prototype that we at SFL put together in collaboration with Netapp, where we wanted to test the Netapp Nvidia integration, as well as some of the functionality of the Netapp Data Science Toolkit. To develop this use case, we looked at the 3D segmentation of lung lesion areas in computed tomography or CT scans. Obviously, over the past year, COVID-19 pandemic has overwhelmed healthcare systems worldwide in an unprecedented manner. And a lot of research has focused on different ways that AI systems can help with this ongoing crisis. In the image on the right, we see the progression of the disease apparent in periodic CT scans of a particular patient's chest. In practice, scans like this can be used to aid the clinical care and treatment of patients by helping healthcare professionals monitor disease severity through time. Additionally, these images can be used as an early indicator of the disease in situations where other means of testing may not be easily available. Now, radiologists are very busy. Research has shown that medical imaging volumes have been growing at a high rate in recent years. In fact, recent estimates say that an average radiologist must interpret one image every 3 or 4 seconds in an 8-hour workday just to meet workload demands. The general idea here is that by using an AI system to aid in the analysis and monitoring of the disease severity, we can improve the efficiency of anyone who's looking to extract information from this type of imaging data at scale. Radiologists, researchers, and healthcare professionals will save time and resources if they have access to fast and accurate means of identifying and tracking this disease in patient scans. To take advantage of the recent advances in deep learning methods and the modern capabilities of AI-enabled hardware solutions, SFL Scientific developed a deep learning model that can automatically identify and segment lesions in 3D CT scans of the lungs. To prototype the solution, we used a pipeline that incorporates a modeling pipeline that is available from Nvidia, as well as the infrastructure software from Netapp. The input data comes in voxel format with horizontal resolution of 512 by 512 pixel and a vertical resolution of between 40 and 360 slices. The image in this slide shows the 3 2D slices of the 3D scan, and it shows the human annotations of the lesion areas on the top, as well as the model predictions showing the accuracy of the model's output on this particular sample. Now, in our use case, we only used the 3D mask output of the model to compare the overlap of the model predictions to human annotations. However, it is also possible to extract the volume of the found lesions using this model. It should also be noted that with the fast data access speed allowed by the Netapp ONTAP system and running on the Nvidia DGX, the model takes an average of only 6 seconds to make predictions on each scan, allowing for fast and accurate output that can be integrated into modern healthcare information systems. Starting with the pre-trained segmentation model in Nvidia Clara, we use transfer learning to train on an additional COVID-19 specific data that has been annotated manually for affected regions. This training process allowed the model to use all of the knowledge already present from the pre-trained model and to further learn on our particular data set and thus increase the model's performance. As some background, there was a challenge called COVID-19 Lung CT Lesion Segmentation Challenge in 2020, which was held to create a platform that evaluates methods for segmentation of lung lesions from these type of images. The model tuning and evaluation results we present was based on the publicly available data set from this challenge. It should be noted that no mention of strain, severity, patient location, or patient demographics are mentioned with this open data set, and no direct medical inference can be made to such factors. Model performance is measured using a DICE score, which is a measure of the spatial overlap between human and model annotations. So here, using the pre-trained model, we see a level of 0.76. And to put it in context, the winner of the COVID-19 Lung CT Lesion Segmentation Challenge from about a year ago achieved a DICE score of 0.67, which means that our simple pipeline using just the pre-trained model is already reaching very high accuracy levels. And as I mentioned, With fine-tuning, it was possible to further boost the model performance with a relatively small amount of custom data. In this case, about 200 chest CT images with human annotations were used for model fine-tuning, and we were able to achieve about a 2.6% increase in the model performance of this already very accurate model. So a little bit of background on the model architecture that we employed in this use case. So this is a type of deep convolutional neural network called 3D SegResNet. This robust architecture that can take a 3D image as input and output a segmentation mask of a particular region of interest. For example, this kind of network structure can also be trained to locate a tumor in the brain or some other type of the body. Some quick background on CNNs. Convolutional neural network is a class of deep neural networks that employ a mathematical operation called a convolution. This operation allows the model to effectively scan small areas and keep track of local spatial relationships that are key to understanding and processing 2D and 3D image data. A CNN makes successive mapping operations to transform pixel inputs into high-level features, and various CNN-based architectures are used in medical imaging-related AI systems. These type of networks are trained by learning from examples, and they demonstrate state-of-the-art segmentation accuracy both in 2D and in 3D medical image modalities. It should be noted that this particular architecture also makes use of more advanced features such as autoencoder regularization and skip connections to achieve its results. More broadly, coming up with a model architecture is a time-consuming and empirical process. Academic institutions and research groups and large organizations make a lot of pre-trained models available for free or as an enticement to use their platform, as is the case with Nvidia Clara. So entities looking to train a model for commercial or public use have to compare the cost and benefit of developing, training, and testing a new model architecture from scratch with using a pre-existing pre-trained model and fine-tuning, which is generally faster, cheaper, and requires less data. So thinking about specific public use cases for the modeling approach that we just outlined, we see several potential ways of integrating into a larger application or system. One of those ways would be an automatic CT scan monitoring system. So here, the high volume of CT scans that are already being recorded and stored by a hospital system could automatically be scanned for lesions. This would help overall monitoring of COVID for potentially asymptomatic carriers who would not have been given a COVID test, but received the CT scan for an unrelated reason. Another way this would be used that I already referred to earlier in the presentation is clinical study treatment monitoring. So here we would track the data from CT scans of COVID patients undergoing treatment and therapy to give more data to the researchers. And this should help streamline and collect the necessary data for the development and approval of new drugs and treatments. And the last use case would be ventilator and outcome prediction. This would require further research and development, but a model similar to this could potentially be used to predict whether a patient will need a ventilator or an ICU bed, which would help hospitals manage capacity and specialized treatment plans for during and after COVID patient care. In thinking about these use cases, there's an important thing to keep in mind here. While building a model can be relatively simple and fast, creating something that is useful and practical is considerably more difficult. So whether it's building from scratch or enhancing and developing an existing AI healthcare system, an organization can save considerable time and in-house engineering resources by filling these three key roles when undertaking any large AI project. Number one is storage. Computer vision-based workloads in the healthcare sector provide unique data storage challenges requiring fast, secure, and scalable storage for large data sets. Netapp provides a full range of hybrid cloud data services that simplify management of applications and data across cloud and on-premises environments. Netapp software and hardware integrate seamlessly with any existing storage systems and provide access to cloud storage and compute resources and allow for cost-effective management of data-intensive workloads. Number two is GPU and AI software. Large-scale AI systems, especially in the computer vision domain, will generally require GPU processors for fast training and fast inference times. Utilizing an existing AI software platform such as Nvidia Clara greatly reduces the cost and complexity of taking a model from the data science team into production and offers a variety of deployment options from web-based APIs to running locally on an edge device. A lot of the best practice, state-of-the-art data science and ML ops techniques and protocols are already created and available as flexible and robust services through NVIDIA's platform. And lastly, an implementation and service delivery partner. An implementation partner with experience in solving operational challenges and building scalable AI systems is paramount in a successful delivery of any solution. A good implementation partner should be able to integrate and support initiatives within existing research and engineering groups, or develop and implement solutions independently based on the project specifics. SFL Scientific is partnered with both Nvidia and Netapp and brings considerable expertise in design and deployment of large-scale machine learning systems. These partnerships and the vast experience in creating custom AI applications puts SFL Scientific in a unique position to provide state-of-the-art service in implementing and supporting even the most complex healthcare AI solutions. Okay, and with that, I'd like to thank you for your attention, and I'm going to pass it back over to Rick now, who'll cover some more specifics about NVIDIA's and Netapp's capabilities in this space. Thank you.
Thank you, Igor. With that, I'll go ahead and talk about NVIDIA Clara imaging framework. The GPU-accelerated AI applications have been playing an increasing important role in medical imaging because of the rapid development in deep learning models and computation power. Nowadays, GPUs are commonly used in most of the imaging edge devices, including CT, MRI, X-ray, and other protocols. With the latest release of the NVIDIA Clara application framework, developers have the necessary tools and APIs to carry out AI development, as well as introduce AI capabilities to medical devices through embedded hardware. Clara includes a wide range of pre-trained models, so customers can get a jump start on a variety of medical imaging tasks. And Clara also provides AI-assisted annotation tool that allows the fast labeling of images, so radiologists and clinicians can effectively share their knowledge and contribute to the development of AI models. You can check out my technical report, Netapp Untapped AI Reference Architecture for Healthcare Diagnostic Imaging on netapp.com for more information on how we use Clara AI server with MITK to perform hippocampus segmentation. It was my first project at Netapp. I loaded brain MRI slices with pre-trained models, annotated extra images for transfer learning, and fine-tuned the model on DGX system. During these extraordinary times, Clara has released a fully pre-trained long Lesion segmentation model, which is perfect for our use case, as Igor just covered. Now, let's look at an end-to-end model development architecture, how we started from pre-trained models to load CT images with annotations and then transform the data for model fine-tuning. This shows a deep learning framework that is optimized for this clinical domain. The solution is based on Netapp infrastructure powered by Nvidia DGX server. This architecture was developed by Netapp and Nvidia. It leverages the compute power of Nvidia DGX servers and is backed by a Netapp Untapped storage system. This architecture shown here addresses the storage needs for the CT images and development requirements of training and deploying the deep learning model. On the left-hand side of the diagram, a pre-trained model is used as the starting point and is then fine-tuned by being trained on the task-specific dataset. Various transformations of the dataset and configurations of the model are experimented, and that resulting model performance is evaluated. The untapped snapshot capability allows for near instantaneous saving and storing of snapshots, which makes this iterative experimentation phase simple and easy to manage. Eventually, the best performing model is selected by the data scientists or clinicians, and we can package this for deployment into a healthcare AI system. Deployment considerations are covered in subsequent slides using NVIDIA frameworks. Next, let's look at benefits of transfer learning. The CT lung lesion segmentation model can identify regions of the lung that are affected by COVID-19. As covered before, we use the pre-trained versions of this model made available by Nvidia as the starting point of our workflow. Transfer learning is the process where a model was pre-trained on a particular task and then reused as a starting point for training a second task. In this case, you can think of it as taking a pre-trained model and then fine-tuned on your different patient populations for different regions. And this transfer learning approach significantly reduces development time for new models. Typically, using transfer learning, a model can achieve the desired accuracy using only a fraction of the data and time compared with training starting from scratch. Direct integration with the Nvidia deployment ecosystem further reduces engineering and IT resources required to use this AI system. And these models are available in Nvidia NGC, Nvidia GPU Cloud. That's a hub for GPU optimized software. And the NGC catalog provides a wide range of options for GPU optimized pre-trained models for a variety of applications and domains, ranging from medical-focused language models that can be used for natural language processing tasks and a variety of computer vision models that can be used for medical imaging use cases like this CT segmentation task. And you can see on the bottom right-hand side, it shows different NGC collections. You have ASR, COVID-19, or Clara Discovery, Clara NLP, and Clara Train, and image classification. In this case, we use the Clara Train COVID-19 CT lesion segmentation, but you have different models for annotation, classification, and x-rays. Now let's see a demo of COVID-19 CT segmentation using Clara and Netapp Data Science Toolkit on a DGX system. We'll demonstrate ease of use, versioning traceability, and transfer learning for data scientists and clinicians like radiologists. I'll hand over to Rupei from SFL. Take it away, Rupei.
Hi, my name is Rupei. I'm a data scientist at SFL Scientific. I have a PhD in physical chemistry and years of experience in data science and machine learning. And today I'm going to walk you through how we can build a state-of-the-art medical AI system. This solution is made possible only through the close partnership between Netapp, Nvidia, and SFL Scientific. I will walk you through how we implement this state-of-the-art medical AI model. And I also give you a brief introduction of what this model is and how well it actually performs. What we build here is a lung lesion segmentation model. And what it can do is that it can automatically segment or identify the lung lesion areas from the CT images of COVID-19 patients. And why it's important is because the lung lesion is one of the early indicators of this disease, COVID-19. This AI model is going to greatly help the healthcare system and reduce the burden of especially radiologists. To implement this model, we first need to set up a Netapp Untap volume. The setup itself is pretty straightforward. The instructions can be found through the link here. It's relatively easy, and I'll not go into the details here. On that Netapp Untap volume, it will provide us with a full range of Untap functionalities, which is very important and helpful to this healthcare-related system. When we have the Netapp volume set up, what we can do here is to set up the environment. Includes the libraries and packages that we need for the development environment. For this, we use a Docker image that's also provided by Nvidia. Through this link, we can download this Docker image that's specifically created for healthcare applications. And when after we download that model, we can run this command to create a Docker container. And we can start building our model inside this container that will give us the environment we need. Now that we have created this environment, we can download a pre-trained Nvidia Clara model. One of the reasons why this whole implementation is so straightforward and can be described in a single Jupyter notebook is because Nvidia Clara has provided us with a range of healthcare related models. And in this case, there is a model that's specifically trained for COVID-19 related tasks. And one of them is directly related to the task of generating the segmentation of the COVID-19 affected lung lesion areas. We can make use of that model and give us a jump start on what we're trying to achieve here. Now we have the model, we have the libraries. The next thing we need to do is to download the actual data we use. So the data we used in this tutorial is from a open data challenge that's for the COVID lung CT lesion segmentation. It contains chest CT images from 199 patients. We can download the data from this link. So by running the cell, the next tool that we are using in this tutorial is the Netapp Data Science Toolkit. It is a Python library that makes it very easy for data scientists to perform data management tasks, such as cloning a data volume or snapshotting a data volume, the traceability of the model and the data. This is especially important in healthcare-related AI applications because we want to ensure the reproducibility of the model. By saving a copy of both the model and the data that was used to train the model, we can ensure that we have this reproducibility of the model, or what we call traceability. We can download this data science toolkit from GitHub. It can be easily configured by following the instructions here. So we can first take a look at the current snapshots on this Untitled volume. We can see that this Untitled system already saves daily, hourly, or weekly snapshots before we have saved any of our own manual snapshots. They provide a way to go back to an older state of the system in case something happened. Now we can take a look at the data set. So there are a total of 199 images. The images are 3D volumetric images with various dimensions. X, Y dimensions are 512, and the Z dimensions are different for different images. That's basically what the CT images are like. Okay, what does a lung lesion look like? Now we can try to visualize one of the sample images. So this is a visualization of one example. We can see that the lesion regions are already labeled by the human annotators, and they're shown in red. It's actually a little difficult for me to tell what they look like in the CT images. They are not such a straightforward task. They might not be too difficult for healthcare professionals, but they are definitely not easy for lay people. So that's what we have, and that's what we want the model to be able to do, to label the lesion areas, like what the humans are doing here. So we need to create an AI model that can do this. We can create a snapshot of the original dataset before any of our training work to save a copy of everything, so we can fall back in case anything happens. This can be done with one line of code almost instantaneously. Now, if we check the snapshots we have, we see we have this new snapshot, the original data. With that, we can now start preparing for the training job. The first thing we need to do is to prepare several data splits. In data science, we often split the data into subsets. And the reason of that is we want to make sure the model does not overfit to the training data set and can be generalizable to the new data. And also make sure in the evaluation, model does not show an inflated performance by evaluating on the data it was previously trained on. By following those commands, we can split the data into a training set, validation set, and a test set. We create and save a JSON file. That's what the Clara pipeline will make use of to identify the images that are going to be used in the training and the images that are going to be used in the test. Now we have the splits. The next thing we want to do is to evaluate the performance of the pre-trained model. The evaluation of the pre-trained model can be done using the built-in script, validation.sh. In this case, it's evaluated on 40 images in the test set. And what we can see is the evaluation of the 40 images took about 4 minutes, and that's only 6 seconds on each image, much faster than a radiologist, and can potentially save them a lot of valuable time and can be integrated in the workflow of a radiologist. Let's take a look at what the prediction look like in the images. Again, we visualize predictions of the model and compare that with the human annotations. And what we can see here is that they look very similar by eye. They're pointing to exactly the same region, going to provide a lot of value for the radiologist to help them pinpoint the area of interest. We can further evaluate the model with a quantitative evaluation, which people usually use dice coefficient in the field. The dice coefficient measures the overlap between the true label and the model prediction. So in this case, we got a dice score of 0.76. Very impressive score. That's not surprising because this pre-trained model was developed by Nvidia in collaboration with the NIH. So this is already a top performing model in the field. By a few lines of code, we can make use of that model and make inferences. So that is the performance of the pre-trained model. What we want to show here is that we can further tune the model to get an even higher performance because we have additional data. We have this data set not seen by the model yet. So by providing the model with extra data, the model can be further tuned to achieve a higher performance. We can also visualize the training progress with the Tensorboard. What we see here is how the model is improving during the training process. As we can see, it's very stochastic. If we increase the smoothing, you can see in the longer time scale, the model is slowly improving. And this is the training loss, or we can think it as the error. And it's also slowly reducing over time. In this case, we trained the model or fine-tuned the model for about 20 hours. If we have more time, we can keep the tuning running and potentially we can get an even better performance. So let's take a look at the performance of our tuned model. Using the same command, we can evaluate the model using the dice coefficient. And what we got is a dice score of 0.78. Comparing to the pre-trained model at 0.76, we are seeing a 2.5% improvement. And that is very impressive because it's based on a already top performing model. When we have this tuned model, what we can do again here is to create a snapshot of the model. This is also what we did before our tuning experiment. After creating a snapshot, now we have another copy of the data and the model configurations at this time point. So if we want to fall back to another model, we still have a copy that's saved. That makes sure we have this traceability of the model, which is very important in the implementation of healthcare models. Again, restoring a saved snapshot is only one line of code here using the data science toolkit. Now we can see we have the original data, we have the tuned model. Potentially we can tune another model using a different set of parameters and compare the model performance. The data scientist can freely experiment with a whole set of different settings, parameters, or pre-processing methods with the data and select the best performing model. And the data scientist can fall back to the best performing model just with another line of code. That is to restore one of the snapshots. They can further deploy that model for the end-to-end applications.
Thank you, Rupei. That was a great technical highlight for the joint partnership among Netapp, Nvidia, and SFL Scientific. Now let's look at how Netapp AI is able to perform AI data management across a hybrid cloud. We have developed and released Netapp Data Science Toolkit to help simplify AI data management. Now, let's look at a typical case of how data scientists perform experimentation. You start from a gold source data set, and data scientists may perform transformations or processings on that gold source data set. Therefore, it is necessary to have different copies of this data set. And then data scientists can perform their experimentations. Here is an example of how Netapp AI is able to accelerate the training workflow efficiently. A simple example is if you have 10 terabytes dataset, and traditionally it will take 17 hours to manually copying the data. By using Netapp Data Science Toolkit, copying a dataset takes seconds instead of hours. And these copies are stored efficiently. For example, 10 copies of each dataset, we can achieve up to 90% reduction in storage space by leveraging Netapp snapshot technology. As AI moves into highly regulated industries like healthcare and financial services, dataset to model traceability, reproducibility is a mandatory requirement. Traditional versioning tools like Git works on code, but it doesn't work with versioning of datasets. Therefore, to achieve explainable AI, we have the solution utilizing existing proven Netapp snapshot volumes. that can quickly and efficiently version your dataset as well as your code. So when regulator knocks on your door, you can quickly provide what dataset and what model is trained together. And snapshot names can be saved in code or model repository to implement such traceability. There are two approaches users can leverage this traceability. It's either in a workflow-driven approach, which is a step in an automatic workflow like a Kubeflow pipeline, or an interactive approach. Users can perform this versioning working in a UI or command line interface. Both ways provide the same Netapp snapshot data management capability. Netapp Data Science Toolkit simplifies AI data management, leveraging Netapp's industry-leading multi-tenant data management capabilities, includes all flavors of Untap. This is designed for data scientists and data engineers because it's simple, easy to use. We have released a portable library of Python functions and also command line interface. This provides access to advanced features that would normally require help from storage administrators. For example, a data scientist can choose to work in a Jupyter notebook, and then by simple few lines of code, data scientists can provision snapshots, clone the dataset or the model, and underlying storage platform is Netapp Untap. It's either on the edge, we have Untap Select, or at the core, we have Untap AI, or in the cloud, leveraging Netapp Cloud Volume Untap. In the middle, we can see data engineers may choose to use a command line interface or work within terminal. Netapp Data Science Toolkit work in this environment as well, and that will help you quickly productionize your model. On the right-hand side, the data team can choose to use automatic workflows like Kubeflow or Apache Airflow. We have integration with these automatic workflows as well. As I mentioned, the key capabilities of Netapp Data Science Toolkit is to rapidly provision a new data volume, near instantaneously clone such data volume, and you can snapshot your volume for traceability and versioning. And you can also trigger data sync. We have Netapp Cloud Sync, where you can specify different sources and destinations. For example, if you have many small files in a S3 object storage, we can push and pull from your buckets to perform this in a multi-threaded approach. We also have Netapp Storage Grid, where you can build a large data lake that spans across edge, core, and cloud. The latest release of Netapp Data Science Toolkit version 1.2 in March is now Kubernetes native, meaning that you can provision, clone, snapshot, and delete Jupyter workspaces, or provision, clone, snapshot Kubernetes PVCs in a simple lines of code. And we also have enhancement to the traditional toolkit, which enables you to pre-populate specific directories on a flash cache volume. The use case would be, as I mentioned before, if you have a large data lake and you want to pre-populate high-performance AI training tier with different data collects among the cloud, then you can use the latest release of our data science toolkit, which will use underlying Netapp Trident technology to work with your data lake and help you with such high performance AI training requirement. Customers have multiple deployment options to leverage Netapp Data Science Toolkit with AI control plan. For smaller teams, this standalone AI data management is easy to use and simple to manage. You don't need storage expertise or any MLOps platform. You can also use Netapp Data Science Toolkit with our AI control plane. It's a full-stack MLOps solution built around popular open-source tools like Kubeflow, Apache Airflow, and its Kubernetes native powered by Netapp Trident for data management. It is very simple to invoke such data management operations within Jupyter notebooks, Kubeflow pipelines, and/or Apache Airflow workflows. For larger enterprises, you can also use our Data Science Toolkit and AI Control Plan with other MLOps platforms. For example, customers might want to use proprietary MLOps platform or a customized version or homegrown MLOps developed in-house. And the figure on the right shows how these different technologies are connected from edge to core to cloud, forming a data fabric powered by Netapp. Lastly, these are the value propositions of Netapp AI. Data fuels AI. We fuel data. We can improve your models by creating an end-to-end pipeline with the best machine learning platform. We enable seamless hybrid cloud AI training and inferencing. You can get a faster ROI from your investments. We eliminate hours and days of configuration. We published Untitled AI verified reference architectures so customers can quickly deploy their AI environment. You can start with a small POC and scale efficiently on premises or in the cloud. We reduce your total cost of ownership. Automated data tiering moves code data to a lower tier that will reduce your infrastructure costs. Finally, we bring your data rivers into a unified data lake. You no longer have to deal with data silos. We eliminate such silos in your infrastructure, serving HPC, Hadoop, modern analytics, and AI applications. Here are some additional resources you can check out. Please visit www.netapp.com/AI. You can see all our different collaterals for different industry verticals, deployment options, and Netapp AI partner network integrations. We have blogs on Netapp Data Science Toolkit discussing how you can accelerate AI training workflow and in details of how it is easy to use this dataset to model traceability with MLflow. We also have blog posts on high-level business value, as well as demo videos to show in detail how you can near instantaneously clone a data volume with Netapp Data Science Toolkit and provision new data volumes. We have solution briefs for different use cases, and we have published GitHub repository for Netapp Data Science Toolkit and our other Netapp AI solutions.
Thank you for joining our session. I hope you enjoy it. Feel free to check out our other AI sessions this week and visit our GTC21 LinkedIn page to engage with one of our AI solutions specialists. You can scan the QR code using your phone or go to ntapp.com/GTC21. The first 150 people to join us will receive a $50